Hello, friends, in the series of learning computer organization and design. Today, we will discuss about logic microoperations. Let's start this session from the overview of the topics that we have already covered and that are yet to be covered. So, we started our discussion for this chapter from the introduction to the RTL, and then we discuss about the resistor transfer. We had a detailed session on the bus and the memory transfers, where we learned that the bus systems can be designed with the help of multiplexers as well as with the help of the tri state buffers, right? Then, after this, we shifted to the arithmetic microoperation in the previous session, and today we will discuss about the logic microoperations. And after that, we will have a focus on these two topics, which are the shift microoperations and the arithmetic logical shift unit. So let's understand about what are these logic microoperations all about. So when we talk about the logic microoperation, the idea is that any logic operation which we are performing on the data which is stored on the registers, I will call them as the logic microoperation in the layman language, right? So what exactly we are doing in these kind of microoperations? So basically, logic microoperations consider that each bit of the register will be treated separately and we will treat them as in the form of the binary variables. So what is my point here? When I will be talking, let's suppose I am having a register A with data something like this, and I want that this and this bit should be changed to 1 and 1. So it means that I want that a resultant resistor should have the value like this. It means I will be treating the bits of the resistor individually and separately, right? And these bits, how I am going to treat them so that I will be able to get this result will be performed through the use of the logic microoperations. For an instance, let's suppose this is the microoperation that we want to perform. This P is a control function, and then we want to perform an operation of XOR or R1 and R2 data. This is the data R1 and this is R2, and ultimately the result again I want to store in this R1 register. So, how I will be able to get that, and what will be the resultant? So if I look at these values, I know that in a simple XOR operation, what will happen? For 0, 0, I will get 0. For 1 and 0, it will be 1. For 0 and 1, answer will be 1. And for 1 and 1, answer will be 0. So ultimately, what has happened here? This is again the content of R1 resistor when the control value this P was equals to 1. So my point is that how the data of R1 is changed to the new updated data. So with the use of this XOR operation only. So this is what is the point here. In the logic micro operations, we will function on the each and every bit. We have to perform some operations on it, and then we have to figure out what is the final result that we are getting after applying the operation. So in the logic micro operations, we are using some specialized symbols. Reason being, this example will actually demonstrate better the reason. Like this particular operation is there. It is a control function. So this control function is simply saying that apply the logic micro operation or on the data like this, right? Only then the data from the R2 resistor will be transferred to the R3 resistor. And sorry, the contents of R1, R2 will be added to the R3 resistor, and then the resultant will be stored in the R1 resistor. So this is the exact idea. But when I will be applying plus here and here also, I might got confused with the thing, which is the logic microoperation and which is the arithmetic one. So in order to demonstrate these ideas in case of the logic microoperations, we are actually using some specialized symbols for and or, because we know that and usually performs the function like of as of addition, right? and or basically performs the function as that of addition, and usually performs the function as that of multiplication. So and will be or will be denoted like this, and by this. All right. So let's learn more about these micro operations in detail. So in total, we are having only the four kind of micro operations, like AND, logic micro operation, OR logic micro operation, XOR logic micro operation, and the last one is there, which is complement. So from these four logic micro operations, I am able to describe the 16 different Boolean functions or the Boolean micro operations from there in context of OR, in context of logic micro operations only. So let's understand in more detail about the logic micro operations. So for your reference, let me tell you, you need not to cram this particular table. Okay, this is just for your understanding that how we are able to perform the different logic micro operations. Like we are doing nothing but the same operations, but on different data or in different ways. That is the point. So, before starting learning in detail about the applications of logic microoperations, let's understand the hardware implementation of these logic microoperations. So, what is the hardware implementation? So, in terms of hardware component, how these are actually connected together. So, we will start from the function table. This is the function table. As I said earlier, we are having only four different basic, you could say that the logic micro operations existing in terms of and, in terms of or, in terms of XOR, and in terms of complement. So if we are having four operations, so definitely I will be using two input values, being it A and B. Okay, and for the first I will be applying and. It could be anything. I just right now I am designing this diagram based upon this function table. So the second one is for OR, then is for XOR, and then last one is for NOT to get the complement. So these selection lines will decide which operation has to take place, and accordingly this multiplexer will operate and will provide me the output here. That's it. So now let's understand that where we are using the logic micro operations. So I said earlier also, logic micro operations are basically used for manipulating the bits in the resistor. So let's understand that how we are able to manipulate the bits or change the bits which are present in the resistor. So logic microoperations can be used to manipulate the individual bits or a portion of a word or in a resistor. So idea here is that if in a resistor A, the data present is like this, and I want to change the values this, then how it could be done? I need to take help of some another resistor. Okay, with the help of this I would be able to make some changes into the given resistor. So this is how I will be able to perform the changes. I would be able to change certain bits which are available within a resistor into the new ones. This is what the point is. So how we are able to do that? First thing is the need is that we need some another resistor B, and the bit data which is present here in the B resistor will help me to modify the data which is present in the A resistor. Now, how I can do this? For this, we are having a number of operations in case of the logic micro operations like selective set, selective complement, selective clear, mask, clear, and insert. Let's understand them in more detail. So, the very first one is the selective set. So, please understand carefully the meaning of the term selective means on the selected data. What I need to do, I need to set the value of that selected data to be equals to 1. Now how I can perform that? Let's suppose I am having a resistor A with the data 1100, and there is a resistor number B, any resistor with the value 1010. Now, if I have to apply the selective set operation, as I said earlier, how I will be able to perform or to make the changes in this A resistor with the help of this B resistor. So what I need to do is I need to look at the resistors bit B. Wherever we are getting in B the value or the bit is equals to 1, I need to check the corresponding value of the A resistor, and as the name specifies, I need to set that value is equals to 1. So what will be the output? This exactly is 1 before. I need not to change this, and this 1 and this was 0. So I need to set this value to be equals to 1, and rest all values will remain the same. Let's take one more example. Let's suppose the value of A resistor is 10110, and the value in the B resistor is 1100 and 1. So what is selective set? I have to look at the bit values B, where in the B I am getting the value is equals to 1. The corresponding bit position in A, I need to set it equals to 1. So if it is already set, I need not to change. If it is not set E to be equals to 1, I need to set it equals to 1 like this. So ultimately, what I did, I get a new value of the resistor A. So overall, I have only changed these 2 bits, okay? But the resultant is like this. So what does this resultant and how this resultant actually came? It actually arises from the logic operation OR. Got it? Similarly is the selective complement method. Okay. So here is the example. In the B resistor, I need to look for the values of B where the B is equals to 1. The corresponding values of that B resistor or the bits of A, I need to complement them like this. So this 1 will be complemented to 0, and this 0 will complement to 1, and these two value being 1 and 0 will remain unchanged here. So this is what is the selective complement mean. Again, I am taking the another example, 10110, and the B resistor has, let's suppose, value 11001. I need to look at the value of resistor B where it is equals to 1, and then the corresponding bit position of A. I need to complement those bits, and the rest values will remain unchanged. Okay, so this is the selective complement method. This is nothing but performing the XOR operation. See, for 0 0 we are getting 0. For the complemented values, so the alternative values, the output is equals to 1, and for the same value the output is equals to 0. In the same way, the next third operation will be performed, whose name is selective clear. Means on the selected bits of resistor number A, I need to clear them to equals to 0. So what does it means? I need to again look at the resistor B where the bits are equals to 1. Then the corresponding values of A resistor, the A bits, I need to clear them. So this 1 will be clear to 0. This 0 is already 0. Okay, will remain 0. This will remain 1, and this will remain 0. So ultimately what I did, I applied one of those 16 microoperations which are coming under the logic microoperation, and I was able to achieve this result. Let's proceed ahead with the next example, which is the mask operation. It is also known as the delete operation in some cases. So, what is this mask all about? Mask will work the similar way as it was selective clear, but there is a slight difference. The difference is that now what the B bit pattern will do, it will be used to clear certain bits in the resistor number A. So here now in the B resistor, instead of focusing on this 1 1, now I need to focus on this 0 0, and the corresponding bit positions of this B resistor, now I need to clear them. So ultimately this 1 will remain 1, this one will be clear to 0, this will be 0 as it is, and this will again further remain the 0. So the idea is that if a bit in B is set to 0, like this, the same bit positions in A are set to equals to 0, otherwise it will remain unchanged. So I hope that you have understood these four logic micro operations. Similarly, we will perform the last one, which is the clear operation. So clear itself means I need to clear the value, but how I will be clearing it? If the bits in the same position of A and B are same, like this, these two bits. If these two bits of A and B, in the bit position, if the bits are same, then I will directly clear them to equals to 0. Otherwise they will be set in the resistor A. Otherwise what I will do, for the complemented values I need to set them to be equals to 1. So this is how I will proceed with this last operation of clear. So it is nothing but an XOR operation. So actually this is not the last logic micro operation. There is one more logic micro operation. We called it as insert micro operation. So let's understand how we are performing the insert logic micro operation. Insert is actually a two-step process. So the number of steps involved are: first, you need to mask a value, and the secondly, you need to apply the OR bits. Now, why the two steps are performed in order to insert a new data? Let's understand that. So here is an example being given. Example says this is the original data which is stored in the register. So now you want that these bits of the A register to be changed with these new bits. Means I need to insert a new data on a portion of the bits which are available in the register number A. So how I could do that? As I said earlier, it is a two-step process. So I will start with the very first operation, which is called as a mask operation. Let's understand how to do that. So previously we have learned that in order to perform mask, what we need to do is we need to apply the 0 0 value, because mask can be performed on the 0 positions, and rest all will be settled to be equals to 1 1 1 1. So what will be the resultant of this? For this 1 1 1 1, this entire data will remain same. And for this last bits, what do the masks do? Wherever in the register number B, in the second register, we are having the bits equals to 0, their corresponding bits, I need to clear them. So I will be simply clearing that. This is what I did. Actually, what is happening here is, in order to insert a new data, I can't insert it directly. I need to clear this data first, and only then, after clearing the data, I will be able to insert the new data. Now is the second step. So in the second step, what I will do, I have to perform the OR function. So let's add the bits. Where I need to add a new bit, I will add it, and rest all values will remain 0 0 0 0, right? So ultimately what will happen, now I will perform the OR operation here. So for 1 0 1 0 0 0 1 0, I will get the same value, and for this 0 1, I will get this updated output of the register number A in the end. I hope that you are able to understand these applications of logic micro operations. So for your convenience, let me explain you this point of insert operation again. So again, I am just taking one example here. In case of insert, let's suppose I am having a register A with the data. I am just picking any random data. Okay. And now I want that these and these bits should be replaced with a new data. Like, let's suppose like this. Okay. So how I will perform this updated data? So again, it is a two-step process. First thing is that I will be writing the data the same 1010 triple one zero triple one zero one zero zero zero. So I need to perform the mask here. So mask will be performed only on this updated content. So wherever I want to update the data, I will be using the value 00 and rest all will remain 1. So how, what is the value I will get here? 1010. I will be able to clear these values. It is 1 here, right? Now this first operation is done, first step is done. Now is the second point when I will be inserting the new bits, right? So how I will be inserting? Where I need to insert the new data? 1001, and this is 01001, and the rest value will remain 0, and then I will perform the OR operation here. So ultimately I will get the new data as it was been desired. So this is what is the output of this insert operation. I succeed in updating or inserting a new value into the system. So this is all about the logic micro operations. Thank you so much for joining this session.